All right. So allow me now to discuss to you our first module. So a short discussion about introduction to model-based design. I already uploaded this one in our LMS, but then again, I would like to discuss some parts of the introduction to model-based design. So basically, our elective subject is model-based design. And as you know, it is a system model at the center of the development process from specification to design, verification, implementation, and testing. So what does it mean? Instead of creating the actual prototype and expending too much cost for you to develop such specific system, so you can actually create a simulation, a specification using models, using building blocks, so that you can test your design before the actual implementation. So we have different functionalities and operations for model-based design. So we needed to use both Matlab and Simulink. So that's why we have separate discussion actually for Matlab and then a separate discussion with Simulink. So for the functionalities, basically, model-based design functionalities include the following. So we can actually create an interactive graphical user interface. We can develop a test bench so that we could verify the system. And of course, we can do system validation. We can optimize because, say, for example, you would like to reduce the number of logic gates. So you can easily do that using Simulink building blocks. And then in this Simulink, you can also design complex control systems. So meaning to say, we're not only dealing here with linear systems, but we can actually do dynamic systems. So we do have experiments on that as well. And then if the time permit us, we can do some automatic code generation, per which you can actually generate a C code, an HDL code, provided that you have enough license or tools for that. And then we can do embedded deployment, because you can actually integrate your Simulink model with the use of Python or even Arduino microcontroller, or what specific type of microcontroller or FPGA board would you like to use. And also, it is a math-based visual method because it makes use of the usage of the MATLAB, because in MATLAB you can do some matrix, you can do some equations and calculations, and integrated software environment because you can actually integrate your system with other system, just like use of computational intelligence. So for example, you would like to do the MATLAB Simulink with fuzzy logic or with neural network, so you can actually do that using MATLAB Simulink. It is used in varied applications, such as in the next slide. But basically, model-based design can be used both for digital, analog, and mixed signals. So we as computer engineers, we know that digital is just a matter of zero and then one. But in analog, we actually are concerned with signals other than zero and then one. And mixed signals, basically, we're just combining the digital and the analog signals. So everything is possible in model-based design. These are some of the applications of model-based designs. So if you would like to search on, you can check that it can be used for automotive, even in motor control, industrial, communication systems, aerospace, mixed signals, as I have said, both for the digital and the analog systems, control systems, and signal processing. Of course, our course is very limited, and we cannot cover everything in this semester. But I think in our course, we'll just be dealing most likely for digital systems and analog systems. Partly control systems, but primarily for digital and analog systems. Model-based design is an important tool to apply in digital design, analog, and mixed signal systems because it provides accurate specifications of the product model being requested prior designing the circuit. So it is capable of testing and validating whether the circuit is in conformity with a Simulink model using but not limited to field simulation, HDL co-simulation, and test bench models. So basically, field simulation or FPGA in the loop and HDL or hardware description language co-simulation These are just simulation tool that you can use to compare your Verilog models or VHDL models with your Simulink models. So it is beneficial to use a model-based design in different companies, just like in our LDP, and it provides a lot of benefits as illustrated in the next slide. All right, so as I add other students, I'll continue my discussion. Basically, these are some of the benefits that we could utilize using MBD approach. Product quality improvement, development time reduction, time saving, error free, no risk, and of course cost effective. So there are a lot of benefits actually for model based design. All right. But basically, in our case, we just wanted to simulate using the provided circuit. So basically, I'll be giving you some specifications, I'll be giving you some circuits, and you just have to realize that using the Matlab Simulink tool. All right, so there are a lot of students who are still unmute as I discuss, so I'll just mute them if needed. Okay. These are basically the key elements in development process. So we have four main processes that we needed to consider as we do the model-based design. So you will create your own plant model, and then similar to Verilog and HDL, we do the synthesis and we do the analysis of the plant controller, and we do some simulations, of course, and we just deploy or program our plant controller. This is a typical interface of the Simulink. So I already taught this one to you last time. So you have to be familiar that you can actually just click there the icon for the Simulink, and then you can actually click the black model so that you can do the design in your interface. So it supports system level design, simulation, automatic code generation, continuous test, and verification of embedded systems. Simulink software requires Matlab to run. So that's why it took you a lot of time to do the installation, and the file size is huge enough, and you needed to have some license to do the installation, right? So you cannot use the Simulink tool without installing Matlab. All right. So Simulink can use the Matlab environment to define model inputs. We can actually store model outputs for analysis and visualization. So you can use the scope or the display block so that you can actually see the model outputs. We can do functions with a model. So in our Simulink tool, you can actually create your own function. So I'll teach you later on how to do that. And then some mathematical operators and functions can also be integrated in your Simulink model. So it's very handy. With Matlab, a lot of things can be done in Simulink. It is a tool for modeling, simulation, and analysis as illustrated below. So you have a lot of applications that you can use for your Simulink model. So it is a tool for modeling because it provides graphical editor so that you can build models as block diagrams. So it's just making a diagram from the interface so you can actually make models already out of it. You can do the bottom-up approach or the top-down design. So when you speak of top-down design, so you start with the specification itself before building the circuit. But when you do the bottom-up approach, I'll give you the circuit and you do the specification. And then, of course, it is a Simulink tool for simulation. So you can simulate in its dynamic behavior using mathematical integration methods. And you can actually manipulate your inputs. So all of the possible input combinations can test your design actually. And then it is a Simulink tool for analysis. So it includes linearization and trimming tools that you can access from Matlab, plus the many tools in Matlab and its application toolboxes. So we have a lot of ways on how we could analyze our design in Matlab Simulink. So it's actually part of our experimentations in the long run. So let's move on. So you can design and simulate your system in Simulink before moving to hardware. So as I have said, before creating the actual prototype would cost you a lot. So you can make a design first using Matlab Simulink. So you can model and simulate your system earlier. You can test early and often. So meaning to say, if you would like to add additional tool in your design, so it's very easy. If you would like to change some designs in your system, it is very easy for you to do that. And if also you would like to automatically generate a code out of your system, so you can also do that in model-based design. So why do we need model-based design? So there are a lot of reasons, but these are basically some of the primary reasons why we do the model-based design, especially in different industries. Number one, it makes use of common design environment. So meaning to say, we as students can easily understand as well the tools that we can utilize in model-based design. So it's very user-friendly, and then link designs directly to requirements. Out of the requirements given to you, you can actually create an executable specification out of the model. We can integrate testing with design to identify and correct errors. So as you can see, we can create test bench so that we can check whether our outputs is within the requirements following the input combinations, following our truth table. And then we can actually refine algorithms through multi-domain simulation. So if you would like to further optimize, if you would like to reduce the number of gates out of your design, so you can easily do that. It generates embedded software code. So as I have said, if you would like to integrate your system with different prototypes or microcontrollers, so you can actually do that. Develops and reuses test suites. So what does it mean? So if you already created a test bench for a specific design, you can just copy that to the other design. If same test bench will be needed. So it's very handy, and it will not take you too much of your time. Generates documentation. Even the documentation report, if you would like to present the simulation results along with the design, you can do that in model-based design easily. You can reuse designs to deploy system across multiple processors and hardware targets. Of course, our subject is just an elective subject. We're not be doing this one for now, but you can actually do this one using Matlab Simulink as well. Okay, so let's move on. So in most of the research and development companies, we do the following model-based designs for the following reasons. Number one, we would like to provide complete and accurate specifications, because the specifications that are available normally are in datasheet or in PDF or in Word file or even in Excel file. So it is hard for you to visualize what is the real specification of your design. But if you can actually use the model-based design, you can visualize. Number two, clear communication and understanding between the requester and the designer. As you know, we have a lot of languages all over the world. And if you would like to convey or communicate with them, English language is good, but it is better if visual presentation will be used instead. Because if you are an engineer and you communicate with other engineers, regardless of language, you can easily communicate visually. Third one, it generates creative value, because if you would want some modifications in your design, so you can easily do that. If you would like to do some improvement, you can easily do that. Number four, it shortens design period and verification time. Simulation time in MATLAB Simulink is fast. So you can simulate easily regardless of simulation time or sampling time that you would like to use. You can already finish the simulation time ahead of time. No design error, thus preventing rework. Since you're not creating yet the actual prototype, you can easily check the error from the design. Thus, it will prevent you to do the reworking. and you can further enhance the quality of your design. And as I have said, so faster design testing and validation. Basically, these are some of the advantages of the model-based design. As I have said earlier, we can accept design specification as Simulink model in our design work. Paper documentation in datasheet, in Word file, in Excel may not provide the complete specifications, and it is prone to mistakes because it is not visually checked. Third one is the Simulink model is accurate specification because of its capability of verification using the Simulink operations. So since you have a lot of test benches, so before you release your model design, so it is already an accurate specification. Simulink model can be simulated in R&D, and R&D designer can understand the specification accurately and deeply because we have same language naman as engineers. So if you know what is a truth table, if you know what is a flip-flop, you know what is an integrated circuit, you know logic gates, so it is easy for you to convey information with other engineers as well. And then lastly, R&D can validate own designated circuit or RTL by comparing the Simulink model simulation result with own design circuit or RTL. So that's why we have the field simulation and the HDL co-simulation in which you can actually counter check your actual circuit design with your models. So these are the model-based development design process. So specifically, so we define the system, we identify what are the components of the system, we model actually the system with the use of equations, and then we build the Simulink block diagram, we run the simulation, and simply validate the results. So a simple heating system is an example. I think we have an experiment on this one. So you can actually break down your heating system with the following subsystems. So when you say subsystems, so basically these are systems within bigger system. So we have the heater subsystem, the thermostat subsystem, and of course the thermodynamic model system. And from out of that system, we needed to identify what are the components that I needed. So the components that you need, so you need to identify what are the parameters. So what parameters will remain constant over time? What parameters are variable or changing over time? And then we also have the states. So as I have said, the variables in the system that change over time. And then of course, the signals, input and output values that can change dynamically during a simulation. So once you already clarified all of those design components, the next thing to do is you can model using equations. So equation could be algebraic equation, or in our case, the logical equations. But if you do some dynamic systems or complex control systems, you might need to use differential equations or advanced mathematics for you to develop the equations. You can actually do the transfer function if you are actually designing, say, for example, a DC-DC converter or a back and boost converter circuit. From these equations, you can now build your Simulink block diagram. So basically, the block diagram, you can just click and drag from the library browser. You can just select there the blocks that you would like to use. And then this is basically just a simple traditional workflow. The traditional workflow before without the use of model-based design is we create the requirements analysis in paper and documentation in Excel. And then we verify the RTL design and circuit from that Excel file. So it's too hard for you to counter check whether your design is accurate or not. But with the use of model-based design, so you can actually use the model to counter check or verify your circuit design. With model-based design, system engineers use models to derive the low-level requirements. So we can model the following but not limited to digital, analog, and RF components of the system and perform design trade-offs in the simulation. Rather than relying on textual specifications, so we make use MBD, a system model, as an executable execution throughout the development. So it supports system and component level design and simulation, automatic code generation, and continuous test and verification, as illustrated in this design workflow. But the challenging part here is the requirements and the research part. The tool itself in Matlab Simulink is very handy, but you needed to understand what are the requirements or what will be the specifications of your design. Without understanding that, so you cannot develop the required design in your models. So you actually need to have a strong background in the requirement space. So in summary, so there'll be no systematic testing if you do the traditional design. So that's why we ship to the new design flow using the model-based design, as it enables the system test and debug from the earliest stage of development. So with the use of model-based design, so engineers can use models as golden reference. So when you say golden reference, it is the ultimate basis or checkpoints of your design. So if it doesn't pass that reference, then your design is not good enough. So there's something wrong with your design. The models are used as an executable specification in the requirement phase, a design platform in the algorithm design phase, a code generation source in the hardware implementation phase, and of course, a test bench in the testing phase. So by reusing the models, system engineers can free to focus on design innovation to achieve higher system performance. So I think that's it for the short introduction of the model-based design. So let's now move on to the experimentations that we needed to perform. For experiment number 2, as I have discussed last time, so I'll be giving now the deadline for this. For experiment 1, I suppose you already installed. For experiment number 2, I think it's better if you could submit by March 12th. I hope you could finish this one by March 12th. So I will no longer explain this again. I already explained how are you going to do the experiment number 2. For experiment number 3, so allow me to discuss this, and you have to submit this one 2 weeks from now. So you still have March 19 to finish experiment number 3. For experiment number 3, you are tasked to design a 4-bit program counter schematic and Simulink as shown below. Then you just have to simulate the results using the display and the scope blocks. Alright. So as you can see here, we have a program counter 4-bit. Alright. And since this is a counter, normally we use flip-flops for the counter for the sequential circuit. So we have 1, 2, 3, and then 4. So we have 4 data flip-flop or D flip-flop. And then we have also here the increment logic. All right. And we also have your the Tristate Buffer and the multiplexer and the reset logic. Not to mention some logic gates that we are already familiar with, like the AND gates, like the XOR gates, and of course the buffer. The buffer, this is not NAT gate, it's a buffer because there's no nibble. We also have an inverter here. All right. And then what are you going to do is you simply have to model this program counter using Simulink tool. And then these are some of the theory that you needed to understand for you to create easily the program counter. And from this program counter, of course, you need to create your own test bench to check whether your program counter is working properly or not. All right. So now I would like to teach you how are you going to create some logic blocks in the Simulink model. All right, because I suppose you're not yet familiar how to make multiplexer, how to make flip-flop, how to make tri-state buffer. But for the logic gates, I suppose you're already familiar with it. So I'm sharing you now my design. All right. So basically, in my example here, I've created a lot of designs that that you would use as you do the program counter. At first, I have your a latch, okay? So a latch is basically a flip-flop, all right, with clock. That's why it's latch. And you can actually get this one from the library browser. All right. So as you can see here, so when I click here, the block parameters is the latch. Okay. So you can actually search on that in the library browser. I hope it can appear easily. All right. So you just have to type your the latch and then simply click and drag here. Okay. So, but I already have my own here, so I'll explain from my design already. So just have to click and drag there. You can actually rename. We have two inputs, the data, and we have actually the clock, and we have the output Q and the output Q naught. So in your logic circuit design, that's why I'm asking you whether you fully understand that. I think I have a module there explaining the deep flip-flop. So basically, the Q here is the similar to the input. Whatever input it is, that will be the output in Q. But for the Q naught, it's simply the inverter of the D. But since it is a deep flip-flop, so state is very important. So we make use of the clock. All right. So here, as an example here, I just have here an input of constant block, which is 0. All right. And then it's very vital that you connect a data type conversion. You can type here for you to know the name, data type conversion. All right. And then, of course, you can search here the data type conversion. Okay, wrong spelling. All right. Okay. So you just have to click and drag again. And then, why do we need to use the data type conversion? Basically, since I selected here Boolean, it will just convert whatever your input is to Boolean. Boolean is either 0 or 1. Because in logic block, it only accepts values of 0 and 1. So it's better to use data type conversion. And then, since I needed a clock, so I make use of a digital clock. All right, so you can use a digital clock or you can use a pulse generator. In my case, I use digital clock and I set a period of 4, right? So if you would like to see the output of the clock, you can actually put a scope here and then you can actually check the results of your scope block. Okay, so it's pulsing like a clock. So depending on your sampling time, so you will decide what will be the period. In my case, I decide the period is 4. All right, so 4 is from this one, 0 to 4. And then high edge is at 2 and then low edge as another 2. All right. 0101 or 1010. And then if you will not connect anything from the output, you can just connect a terminator or a display block similar to this one. So as you can see, as input 0, the output here of Q is 0 and the inverter Q is 1. So you now have or you now learn how to make a deep flip-flop. So you can just customize this one. You can make 4 deep flip-flops to model this kind of design. Next. All right. So this one, I just created a Matlab function as I explained earlier in our discussion. So you can create your own Matlab function if you would like. So similarly, you just have to type here Matlab function. Right, then simply click and drag. And then as you click and drag, this will be the input and this will be the output. You can further customize that one if you would like to add another inputs. So there's no issue on that. Say for example, you would like to add, you just have to double click and then you can add additional inputs here. Or you can just easily connect. Say for example, you have probably 2. Yes. Okay. It automatically creates no inputs if you would like to connect another input signal to this one, similar to the output. So it's very handy. So in my case, I have an input of enable 5. Then I have a function And the function just makes use of like a simple buffer. Whatever the input is, that will be the outputs. Of course, it's just a simple example of Matlab function. You will learn a lot of Matlab function in the long run. But for now, you can use the Matlab function from the library browser. So it's very easy. Okay. All right. So I think this is the same example as I explained. All right. This one, if you would like to make an if-else statement. Okay. So if you will create an if statement, of course, you know how to make Verilog models and C language already, so you're familiar with if else. You can actually do that in MATLAB Simulink as well. So when you right click here, so if action subsystem, you need that. And then properties, you also need to use if block. All right, so remember that. And then I use a merge block. Okay. And then, of course, these are just the inputs and the outputs. So similarly, it's very easy if you would like to add additional inputs. So you just have to create one and then you can select there anywhere if you would like. But for this example, I just have two. And then you can modify the expression here. So U1 is equal to 0 and U2 is equal to 1. So there are two inputs. If you would like to make it 3, then of course you just have to modify here. And then, meaning to say, if this expression is satisfied, then you have two possible options. So one option is here. Your output 1 is just equal to input 1, which is 1. Else, just an equal also. Else, the value of output 1 is 0. Alright? And take note that you need to use merge so that you can actually combine whatever is the possible output from your if-else statement. So you can combine the outputs from here or from here because either way, you will get the output of 1 following our condition here. So it's just a simple if-else statement. If you would like to create a ladderized if-else statement, so you can just actually include additional inputs here and additional if action subsystem below. So it's very easy. All right. And then one challenging part is the Tristate Buffer. As I have said, the tools are already available, but you needed to understand some requirements before you develop the model. You need to understand first what is a tri-state buffer. So this is basically the tri-state buffer logic symbol. We have the input, we have the output, and we needed to use an enable input here. So that's why we have our enable, so 0011, and then we have input 10101, and we have the output 01ZZ. So when you say Z, meaning to say it is high Z. All right. And then how am I going to do that if you will model this? So you can basically use a switch. So I just use a switch, yan, switch. Just have to select from the library browser switch. And then as I have said, so you have their input like this. So the criteria here is that U2 is greater than the threshold. So this is the U2, this is the U1. It should be greater than the threshold. If it is greater than the threshold, then the output will be the U2. All right. But if it is not greater than the threshold, then the output will be the U1. And take note that in Simulink, we don't implement high C. So if the value is Z, we can just regard that one as 0. Again, instead of displaying the output C, we output 0 or ground for the high Z. So it's up to you. You can actually use a switch, or you can use if else statement, or whatever tool that you would like to use. All right. So, and then I think this is an example that I use in which you can create a subsystem if you would like. So this is basically a subsystem. So how are you going to do the subsystem? You just have to simply highlight your design, and then you can put your designs inside. So just like this one. So I have here D flip-flop 2, D flip-flop 3. So example. So I already have here a D flip-flop, right? So I'll just copy and I'll try to make a subsystem out of it, right? I'll just remove here the connections, okay? And then I'll just copy again, and then another one, and then you can just highlight and then right click and then create subsystem. Okay, right. So when you create subsystem out of it, when you double click, so the systems that you have created are now part of a bigger system. So that's why in most of the designs, if you would like to search on, you can see a bigger system. And then when you just have to double click, then see the subsystems inside. Then the input ports and the output ports are automatically generated. When you double click here, if ever, there'll be some designs inside. But in our case, I don't created designs inside another flip-flop. All right. What else do I need to further explain? Multiplexer. Yes, multiplexer. All right. For the multiplexer, again, for the multiplexer, you just have to understand the truth table. So I suppose I already had given you an experiment on the multiplexer. All right. So for the multiplexer, as you can see, we have four inputs and we have two selector. Okay, and then the output is connected to a demultiplexer, which requires you two selectors again and four outputs. Okay, and this one is the design that I have created for the multiplexer. When you click here, it is just a MUX, so it's readily available. A logic block for the multiplexer is already available. Just have to specify the number of inputs. In my case, I have four. And then you just have to put here what are the values for your multiplexers. For example, this is 4 bits. So I have D0, D1, D2, and then D3. So again, it follows the example here because I have here a multiplexer. So you just have to modify the multiplexer that I am presenting right now. And then when you use the multiplexer, you need to connect that into a selector. Okay, so the selector, you just have to select selector from the library browser and then specify the number of dimensions. So I specified here 1, and then you have to specify the index vector dialog. So 2, this one is 3, and this one is 4. Right. So if you can actually put a display here, and then what does it mean is that if the selector is for DO, then of course the output will be the whatever input it is for the DO. And of course, if the selector is for D1, then D1 will be the output. If the selector is for D3, of course the output will be 3. And if the selector is for the D3, then the output will be 4. So that is the simple implementation of the multiplexer. All right. So I guess you are now capable of creating the experiment number 3. I will now stop the recording so that it will not avoid too much of your time watching the video, and I will entertain the questions afterwards. Any